The sheet from Friday. Number 1. Aiden says number 1 to start with. Just to see. Several of you that asked for help on Friday, I wrote SADMAP at the top of yours because we're still doing that same process of SADMAP, right, and getting that variable by itself. So what do I need to do first? Subtract 6 because it's that addition subtraction. That's exactly right. All right, now I've got b to the 5/6 equals what? There you go. No. You're exactly right, though. You're exactly right. 6 over 5. So what? Remember, we're raising to a reciprocal. We need that to cancel out, so we need to raise it to something that will cancel the 5/6 out. So Brian says 6/5, because when you have a power to a power, what do? Y'all know this. But what do you do when you have a power? You multiply. And when you multiply reciprocals, what do you get? 1. So this becomes b to the 1st, which isolates it. But now the question is, what's 32 to the 6/5? So now you got to rewind back to those radical properties. Remember, sunshine? What's it look like? Close. The other way around. Not the 6th root, but the 5th root. Remember, the one in the bottom is the root, so the 5th root to the 6th power. So the 5th root of 32 is, okay, so you're giving me the whole thing, but what's the 5th root of 32? It's 2, and then 2 to the 6th power is 64. Absolutely. So, because remember, and we got a test on this Wednesday, right? So this goes back to that very first lesson where whatever that, let's say I have x to the, let me write this way first. Let's say the nth root of x to the a. We can write it this way, or we can write it this way. So it doesn't matter if you do the exponent first, and then in other form, those are exactly the same thing. Going back to you a little bit. It doesn't matter. It doesn't matter. That's what we were saying. It doesn't matter. You can put it on the outside or you can put it on the inside, whichever. But because I hope at this point you recognize the 5th root of 32 being a perfect root, you would do the root first and then raise it. Well, I'm not sure. Yes. Is it a flip one? Oh, I see what you're saying. Okay. This was probably one of the harder ones on the sheet, and it came at number 2. But I'm still going to follow the same operation. So the first thing I need to do is get rid of what? All right, SADMAP. So multiply. What's being multiplied, Aiden? The 5. So to get rid of that, what do? You divide -5. But because there's this fraction over here, instead of dividing -5, what's a little bit smarter for me to do? There you go. That's right. So you're right. 1 over 5. So times, yes? So keep the negative, yes. This is going to cancel, but what's going to happen? Look, you got a negative times a negative, right? So I've got x to the -3 over 2 equals 1 over 12. Does that make sense? Now what? I got to get rid of the exponent, so what do I do? So negative 2 over 3. Now I think this was your question. All right, this is gone. But now, because this is negative, it's going to flip this over. So this is the same thing as saying 512 to the 2/3. So you can flip the whole thing and just make it positive. Does that make sense? Okay, so now it's a little bit easier to work with, right? So now I have the third root of 512 squared. And again, if you put that squared under it or you put it outside, it really doesn't matter. So. What? Well, so if you're on your calculator, yes. But here, you're talking about like that. I mean, you could, but then what's going to happen? You're going to have 1 to the negative 2/3 and 512 to the negative 2/3. And then you're going to kind of swap places and become positive. But if you want to go about it that way, that's fine too. You'll still come back to the same thing. And then what's the third root of 512? 8. And 8 squared is? Do I? Really? Interesting. Supposedly it was random, yeah. 14, sure. 14. 1, 2, 4, 9, 4 equals negative 6, 4 into the 5. What do I do first? What do I need to get rid of first? The 6, so I add that to both sides. So I get 1, 2, 5, 0, 0. Now what? Divide by 4. And I get 3, 1, what? 25? What now? Reciprocal, that's exactly right. That's really the only new part. We talked about it briefly, but we didn't really do it. But we're just getting rid of those fractional exponents. Fifth root of 3125 to the third power, which gives me what? I don't know what that comes out to be. I don't know what the third root of 3125 is. Anybody know? 18? I was going to say, no way. It's 5 to the third power, so it's 125. Aiden Everly the jokester. 18 times 18 is big already. Yeah, 19. Better save your dollar so you can go to the basketball game Friday. You better save your dollar so you can pay to get in the basketball game Friday, 4 o'clock. 5a over 8 to the 4/3. So I'm going to divide by negative 5. What's negative 80 divided by negative 5? What? Negative 80 divided by negative 5. 16. I was like, what are y'all talking about? Okay. So, what you mean? Now raise it to the reciprocal power. What's the fourth root of 16? And 2 to the third is? It's 2 to the third, which is 8. So I got 8 equals a over 8. Now, times it by 8, so you get That's that's what Brooklyn was saying earlier. It's the whole unit. So we're gonna do a review tomorrow. Absolutely. All right, what else on this sheet? 13? 13 and 7. 13 and 8? All right, I'll start with 13, then I'll do 8. All right, negative 874 over 125 equals negative 7 plus a to the negative 3 over 2. Add 7. I'm assuming this divides evenly, does it? To this fraction. It doesn't? So I would take my calculator then. What are y'all talking about? Okay, so take out your calculator and do negative 874 divided by 125 and hit enter. And then do plus 7 and then hit math, enter, enter. 1 over what? Well, that's quite convenient. What? Did you not get that? Let me see. All right. Now what? Typical, flip it. Y'all are both exactly right. Negative 2/3. Negative 2/3. Oh, okay. I'm just glad you're into it, Aiden. Like you're paying attention and you're. So that means the negative makes it flip. So really, this is the same thing as 125 over 1 to the positive 2/3, which is nice because this means the third root of 125. Wait. That's got to be like 5. You're exactly right. And then 5 to the second power is on fire. All right. Anything else on that sheet? 8. 729 equals negative 9 minus 5x to the 1/2. What should I do first? Did I write it wrong? I'm sorry. Sorry. What are you distributing? Can you do that? Why? Look at the sign in the middle. You're adding or subtracting inside the parentheses. Exponents never distribute. All right, so let's back up. What can I do now? If you're adding or subtracting inside parentheses, you never distribute yet. Absolutely, because if I think about SADMAP, exponents and parentheses are last, right? But parentheses is dead last. So I can't do anything inside parentheses until the very last thing. So I have to work outside the parentheses first. And you're right, this exponent is outside. So I'm going to raise both sides thirds. That way, Sound effects are free. And I hope that is a perfect third. 81. So it's 9 squared, which is 80. Now, is that something you can solve? Certainly hope so. Add 9. Divide by -5. Negative what? They look terrible, but they're not that bad. All right, do y'all need a stretch break or a brain break before we start inverses? That way? If you want to grab it. All right, let's talk about inverses. So on here, it's referencing R. A lot of times we use f of x, as you know. But if it's R, the inverse of R, if R is some relation, maybe not even a function is why we don't have it as f of x, then to note its inverse, we do a little -1 exponent. So on your sheet, the inverse of a relation R is written as this. We don't read it R to the -1, we read it the inverse of R. So if you ever see that, that's exactly what that means. Have y'all talked about inverses before, maybe in Algebra 1? Yeah? No. Do you know how you find an inverse? No. Okay. Finding an inverse is really, the concept is really easy, okay? Finding an inverse just means switching x and y. So literally, if I have a set of points, I just switch the x and the y, and those are the inverses of each other, okay? If I'm talking about on a graph, if I switch the x and the y axis, which essentially just rotates whatever it is you're graphing, then I have the inverse, okay? So all I'm doing is switching x and y. Now, there are special kinds of relationships, which we call one-to-one, and what one-to-one means is one. You have a relation that's a function. So the relation is a function. Now, what does it mean to be a function? We talked about this before. What's it mean to be a function? Nobody remembers? One and only one output for each input. In other words, every x can only have one y that goes with it. We talked about the vertical line test here. Do y'all remember all this? Vertical line test. To see if it's actually a function. So if I had something like this, yes, that's a function. But if it flipped over on its side, and I say that now because that's what inverses are going to do, this is no longer a function because if I drop a vertical line through it, those x's have more than one y that go with them. Okay, it hits that vertical line more than one time. So what one-to-one means is that not only is the relation a function, but also its inverse is a function. So if both the relation and its inverse are both functions, then we say that function is one-to-one and it's very special. It doesn't happen often, but it does happen sometimes. So we're going to do several examples and we're going to talk about, is it a function or not, and is its inverse a function or not? So look at the very first set. The very first set, we've got this relation R. which is 1, negative 2, 4, 3, negative 1, and 4, negative 2. So the first question is, how are we going to find the inverse of this relation? You just switch x and y. That's exactly right. So the inverse is going to look like negative 2, 1. What's the next point going to be? And then negative 1, 3. And then negative. Anybody confused on how we found that inverse? Just from a set of points. Is R a function? How do you tell? That is a good point. You said yeah. Why do you say yeah? Were you saying yeah, how do you tell, or yeah, it is a function? You were saying yeah, how do you tell? Okay, so because all the numbers are different, I know it's got to be a function. So if you think about this, and whenever I get confused, I have to think about it on a graph. If I've got 1, negative 2, 2, 4, 3, negative 1, and 4, negative 2, there's never a place on here where they're directly above each other, right? Where they have the same x value for just that one, because every x has to have its very own unique y value. So here I would say yes, that's a function. When I switch them up, though, do they still retain its functionality? So is it still a function? Why? These 2 points here, right? If you graph those, if you have negative 2, 1, and you have negative 2, 4, look what happens. They're directly on top of each other, right? It would fail the vertical line test, okay? So the relation itself is a function, but this one is not a function. So is it one-to-one? No, because I have to check both of those in order for it to be one-to-one. Does that make sense? Okay, let's look at the second one. So I've got 1, 5, 1, 6, 3, negative 4, and 4, 9. So you all write that inverse for me real quick. Let's see what you So far it's kind of easy. Good. I hope you say that by the end of the lesson. It's not, because in order for it to be one-to-one, we have to check both of them. That's exactly right. This one's flipped, Aiden says. Flipped how? Oh. So there's my inverse, and all I did was swap x and y. He said that R is not a function, but the inverse is a function. Well, okay, so let's look. These 2 ones fall in the x category, right? So that means for the x value, when x equals 1, there are 2 different y's that go with that. I can't have that. I can't have 2 different y's. If this is 1 for 5 and 6, I can't have 2 different y's for the same x. But I can have the same y for 2 different x's, because this would be 5, 1, and 6, 1. So they line up horizontally instead of vertically. So this one is not, but you're right, this one is. Do you see the difference there? So what you're looking for essentially in a set, I'd like you to understand why, but what you're looking for in a set of numbers is if the x repeats, you have the same x, then it's not a function, but you can have the same y. So is it one-to-one? No, it's not one-to-one. 3 is a typical standardized test question. You've probably seen them all over standardized tests before. It's what we call mapping values to each other. So you have these circles, right? This is x, this is y. We have 0, 1, 8, 11. We have negative 5, 2, and 6. What this is saying is when x is 0, y is 6. So 0, 6 is a point. And then when 1 points to 2, that means 1, 2 is a point. 8's not pointing anything, but 11 is pointing to 6. So what it's saying is this is my R, is all that's saying. So what would the inverse look like? Is R a function? Yes. I have the same value, but it repeats in y, not in x, so I'm good. Is the inverse a function? No, because the 6 is repeating in x. Now, we use vertical line tests to test whether or not it's a function, right? We've talked about that extensively. I can easily look at the graph and tell if the inverse is a function by using the horizontal line test on the original function. So in other words, remember this one, or let's just look at a parabola to start with. I know this is a function, it passes the vertical line test anywhere I go. A vertical line is never going to hit it more than once. But if I change that to a horizontal line, it hits twice. So vertical line test tells me whether it's a function or not. But the horizontal line test tells me if the inverse is a function or not. So here, what this would tell me, because I can drop a vertical line anywhere, this would say, yes, this is a function, but its inverse is not a function because it fails the horizontal line test. So the horizontal line test is used to determine whether the what of a relation is a function. The inverse. That's exactly right, the inverse. Look at the first graph. I've never given my kids guided notes for this before. This is always a lot to write. So y'all are welcome. Look at all that you don't have to write. So the question, you're welcome. The question is it a one-to-one? So I got two things to check for one-to-one. What are they? Vertical line test and horizontal line test. If it passes both, it's good. It's one-to-one. If it fails one of them, just one of them, it's not. So this one passes the vertical line test, yes. There's nowhere that I could drop a vertical line where it wouldn't intersect. And it also passes the horizontal line test. So yes, this is one-to-one. How about that next one that looks a little something like this? No. Which one fails? The horizontal fails. So this is a function, but its inverse is not a function. So it's not one-to-one. Still pretty easy for you? Yay! Let's do algebraically then. Here we go. You are right. Here we go. All right. I told you a lot of times we use f of x. So the inverse, if f of x is my relation, then the inverse is written as, and this is where it's a little bit different than just that -1. We put that -1 before the parentheses x, okay? So this is what the inverse of f looks like. There are some steps there for you, and it is the exact same steps I give my students every year in order to algebraically find the inverse. Okay, remember f of x is the same thing as y, so we're going to switch out f of x for y. We're going to switch x and y, and we're going to solve for the new y. Okay, and that's going to give me my inverse because that's all inverses are doing anyway is switching x and y. So look at number 1 or number 6. F of x equals 5x. Okay, well, f of x, I can't switch x and y because there's not a y in there. So I'm going to say, okay, well, really this means y equals 5x. Okay? Switch x and y. And now how do you solve that for y? Just divide 5. Y'all looked at me like that was a trick question. It wasn't. So here, x over 5 equals y, or 1/5 x equals y. Either one of those is okay. And now I'm going to go back to function notation. Since that's the way they started me on the problem, that's the way I need to finish the problem. So I'm going to say the inverse of f is equal to x over 5. That's it. You ready for the next one? Let's look at number 8. 7 is super easy. So let's move on to 8 because it's a little bit harder. I have f of x equals x minus 8 over 3. What do I do first? Change f of x to y. Now what? Switch x and y. Nothing too mathy so far, right? Change f of x to y, switch x and y. Now comes the algebra part. Multiply by 3. Good job, y'all. I thought that was going to trip you up. Add 8. And now just change your notation back. The inverse of f is equal to sorry. Let's do 11 and then we'll verify. We have to finish this, verify, and graph, and we'll be done. This is a kind of a loaded lesson, but it's the last one. It all uses things you already know. There's not a lot of new stuff. It's just understanding what to do with. I say 11 because 11's a little bit harder. Not really, but kind of. These, you're really just writing what you're doing. There's not a lot of simplification with these. It's coming up with a whole new equation. So again, y equals switch x and y. Now the solving here is what's probably going to get you. So what do I do first? Add 6. That's exactly right. So I've got x plus 6 equals y plus 4 cubed. Can I distribute there? Y. A plus in the side means I can't distribute that exponent. So, but I can take care of it, and it's super easy to take care of. How do I get rid of it? I could do the reciprocal. You're exactly right. So I could do one of two things, and they're both doing the exact same thing. I could do the reciprocal on both sides, or I could do the third root. If some of you wanted to do the third root, that works there as well. Okay, and it's the exact same thing. But since the reciprocals are fresh on our mind, we'll do the reciprocal here. So x plus 6 to the 1/3 equals y plus 4. And that 1/3, of course, is the same thing as the cubed root. So if you wrote this as, it's my friend Fred. If you wrote this as the cubed root of x plus 6, y plus 4, same thing. Now all I have to do is what? solve, move that 4. So x plus 6 to the 1/3 minus 4 equals y. Of course, it could be cubed root if you'd rather. And I'm just going to change the notation here back to function notation. Because I am adding in the parentheses. If the only time exponents distribute into parentheses is when you're multiplying or dividing. Other than that, you have to figure out something else to do. Yes or no? Okay. This next part is probably the worst of the lesson. I apologize ahead of time. Do y'all remember composition? Okay. Let me run you through composition real quick. So this is a little sidebar. If you want to write this off to the side or somewhere like that, because you'll need to know how to do this. If I have this equation, I say f of x equals 2x plus 3, for instance. If I asked you to find f of 1, tell me what you would do. Plug in 1 for x, right? 2 times 1 plus 3. What if I asked you to find f of k? What would you do? Same thing. So this is 2k plus 3, right? What if I asked you to find f of x plus 1? It becomes, well, what you do, whatever is here is what's replacing that x to start with, okay? So instead of x, it's x plus 1 plus 3. Well, where composition comes in is I'll define two different functions. So maybe I say, yes, f of x is 2x plus 3. Well, g of x is, we'll say, x minus 5. And then I might say, what is f of g of x? Well, what that's saying is it's saying take g and replace every x in f with whatever g is. Well, what is g? X minus 5. So this is the same thing as saying f of x minus 5, which is exactly what I did here. So the point of this is that whatever is in parentheses is what's replacing every x. Y'all don't remember doing this? You should have done it in Algebra 1, but that's okay. No, okay. So this is 2 times x minus 5 plus 3. Can everybody in here see how that's being plugged in? What's happening there? That's the biggest thing I need you to understand how to verify. And f of g of x is not necessarily the same thing as g of f of x. So if I asked you then to use these same f and g's, come on. Okay. Too much. And I said, what is g of f of x? What would you do? So what is f of x? So tell me what you think g of f of x is. Look at g. Instead of x, it's, and the minus 5 is still there. And of course, I could simplify this down and combine like terms, but I want you to see how we're plugging in here and what we're getting. Is everybody okay? Somewhat. Say that again. Yes, it'd be, yes, you can, because the square root of 9 is, oh, no, wait, no, because you have the plus in the middle, so no, yes. Okay, let's do another of these compositions. There's a blank page, the very last page is blank. You might want to flip over there. I think I need to take just a minute to further explain composition just a little bit. Let's switch up our f and our g. Let's say f of x is 1/2 x squared plus 3, and let's say g of x is x minus 1. See if you can figure out what f of g of x would look like. Everybody agree with that step? So that all I did was, what is g of x? G of x is x minus 1. Okay, so now I'm going to look at f, and everywhere f has an x, I'm going to replace it with x minus 1. No. So what's going to happen, I've got 1/2, and I always think about my x being in parentheses because it'll help you. So it's x minus 1 squared plus 3. Okay. Now, if I needed to expand that out any, I'd be in a FOIL type situation, but I'm not asking you to do that right now. Right now, I just want to make sure you can plug in this way. That's it. That's composition. Yeah. Okay, so what is g of f of x? Okay, so we'll always work inside out here. So furthest inside is f of x. So replace it. What is f of x? 1/2 x squared plus 3. That minus 1. That's exactly right. Because g is x minus 1. So it's not x anymore. It's 1/2 x squared plus 3 minus 1. Yes, yes. It's a little bit different. Whatever's on the outside, that's the equation you're plugging into. Well, because it doesn't equal x minus 1. G is x minus 1, right? Let me show it to you this way. Let's say here is x. Oh. All right, this is x. I was trying to make like a highlighter so you can see. X minus 1. But the x is being replaced with all of this. So that goes into g for the x. Here is the same thing. It's 1/2 x squared, but my x is whatever that g was. So it's 1/2 x. So the equation is still there. It's just the x that's being replaced. Does that make sense? Are you all okay? Okay. Now I want you to look at this one. So this is coming in under number 12. I'm not going to answer the question above number 12 until we do number 12, and I'm going to show you why. I've got f of x equals x squared plus 8, and I've got g of x equals the square root of x minus 8. Okay? I want you to find and simplify this time f of g of x and g of f of x. I want you to find both of those and simplify it and see what happens. Yes. I don't think we're going to make it through this whole lesson today. We might. All right, let's do the first one. F of g of x, so I'm going to replace inside because I'm going to work inside out, right? So f of the square root of x minus a. Okay. Remember, think about this x being in parentheses. It'll make it a little bit easier for you as you go. So this would be the square root of x minus 8 squared plus 8. Everybody on board? Everybody see where that came from? So now I know that the squareds cancel out, right? So it's x minus 8 plus 8. Well, what's negative 8 plus 8? 0. So this just equals x, right? Does that make sense? Say that again. You could if you wanted to, but then it cancels out still. Let's go the other way with it. So g of, instead of f, I'm going to have x squared plus 8. So the square root, x squared plus 8, and then that minus 8 is still there. What happens first? What do you think happens? The 8's cancel out. I need to work under that radical first because that radical groups things together, right? And so I need to stay under there and see if anything simplifies under there. So this gives me the square root of x squared, which cancel out, which leaves me with, look at this. Coincidence? No. Well, if they are inverses of each other, and this is where we're going back up, two functions, f and g, are inverse functions of each other if and only if. That means it's got to be, both parts have to be satisfied. This has to simplify down to x, and this has to simplify down to x. So f and g are inverses if and only if f of g of x equals x and g of f of x equals x. Every single time. So those are your two blanks there above. So f of g of x equals x, g of f of x equals x. So if you plug each one of them into each other, they both simplify down to x. I think we'll work number 13 and stop for today because even though the graphing is super easy, we might do one graphing. We'll see. We'll see. You think it's confusing? Is it the composition that's hard? The composition. Y'all never seen composition before, even though you should have. Yeah. I wish I'd just done a lesson on composition today. Yeah. All right, so to verify these, I need to show that f of g of x equals x and g of f of x equals x. Now, if they don't equal x, then they are not inverses. Okay, so don't assume you did something wrong if they don't. It just means they're not inverses. So let's start with f of g of x. So I'm going to take g here, right, and plug it into f. So x over 4 minus 5. So I've got negative 4. I'm replacing this x with that g, right? But everything else stays. So negative 4, not x, but g plus 5. Are you all with me? Now let's clean it up a little bit and let's see what happens. What is negative 4 times x over 4? Negative 1x, right? So I've got negative 1x. Negative 4 times negative 5 is 20. That's what f of g of x equals. Now, I can stop right here and go, they're not inverses. How do I know? How can I stop right there and say they're not? It didn't simplify just to x. In order for them to be inverses, both of them have to simplify down to just x. Does that make sense? Because it was negative 4 times x over 4. So I don't have to show the other way. Now, if this had equaled x, I want to go in and show the other direction also. Let me just talk to you about graphing for just a second because it's easy. I don't want to leave that hanging over for just one day. You've got the example on here is a triangle that's formed by points in the relation. Okay, so of course to find the inverse, what are we doing? Switching x and y, right? So they want you to graph it. So you graph those points and you get this triangle. Negative 1, 6, negative 7, 2, and then negative 5, negative 3. This is not exact. This will be a little more exact, but I got this triangle, right? If you graph the inverse of that, so if I switch all the x's and y's here, I end up with 2, negative 7, right? Here's 2, negative 7. Negative 3, negative 5. And 6, negative 1. Rough estimate here. But what do you notice happened? What does it look like happened here? It looks like it rotated or maybe reflected, something along those lines, right? If you think about the x and the y axis actually switching places, that's what's happening, okay? And it does end up looking like a rotation on its side, like a 90-degree rotation. So here's what you're going to be doing. You'll take each function here below, and there's 2 lines and 1 quadratic there. And we'll just do the first one together. But yeah, the points, that's just a listing of the points. And that was just a shape so that you could readily see it a little bit better. This one is a line. Okay, so the first thing I'm going to do is find the inverse. So we go back to what we did algebraically. If y is 2x plus 8, how do I find the inverse? Switch x and y and solve, right? Subtract 8. I know that this one's a little bit fast. This is kind of the easy part. Yeah. So remember, I can kind of take this to both. So this is like x over 2 minus 4. And this is going to be my inverse. But when you graph them, you can do whatever you want. If you want to graph the line the way you know how, the original line, up to 8, what's the slope? What's the slope of that line? 2. So up 2 over 1. There's f of x. If you want to take these 2 points, this is 0, 8, and this would be 1, 10. If you want to take those 2 points and just reverse them to graph this next one, or if you want to graph it the way you know how to graph a line, it doesn't matter. You should get the same thing. Down to 4, and then the slope of this one is 1/2, so up 1 over 2. Yeah, but it should be that if you did this correctly, this point should be 10, 1, and this point should be 8, 0. So if you want to, however you want to graph them, if you want to graph them by the equation, or if you want to just graph the first equation and then invert the points, either one of those is okay. But you'll get the same, you should get the same picture there. All right, I'm going to stop because I know that that was a whole lot. I want you to